All right. Patrick, is that Titan as your avatar? Awesome. Titan may be the most interesting place in the solar system. Okay, let's see. Let's look at manage participants, put it there. All right, I'm going to share my screen. Minimize that. View, full screen mode, and go to there. All right, start it on my other device so that I can write. Okay. All right, let's get started. So we're going to do a few things today. First, I want to say something about last Thursday's homework, a question that came up on a lot of them regarding the minimum spacing between peaks. Then we're going to talk about diffraction and interference of light, basically at the level of 25-30. We're going to do some rather simple, exactly solvable cases because they illustrate the technique. And then on Thursday, we'll take that information and use it to talk about the diffraction pattern of a lens. And then after we've done the simpler cases today, we'll talk about a lens system in Zemax. We're going to go over a microscope objective that has very high resolution, much better resolution than the lenses you were studying in the assignment due today. And we're going to talk about how to analyze that, how to combine it with a tube lens. All right, so I asked you guys last time, what is the smallest possible spacing between peaks? And a lot of people said 2 pi over delta k, or 2 pi over 2k, because if you have one of the waves going this way and one of them going that way, then delta k is twice the length of the k vector. And so you get lambda over 2. But other people said 0. And I think the rationale was, look, 0 is the smallest possible absolute value. Sure, but the only way you're going to get that is if the two waves are going in the same direction, so that when we do the time averaging, it's just flat. And well, a flat curve, you could in some sense say that every point is a peak or none of the points are peaks. It gets into a philosophical discussion, but it carries no information. There's no spatial variation. And it turns out that this goes to a more important point about what is the optimal pixel size. What is the largest pixel size you could possibly get away with? And in general, smaller pixels are better, because even if the pixels are so small that you're not getting much signal on each individual pixel, you can always add up the signals from multiple pixels. You can always start off with something that's very fine-grained and then build up to something that's coarse-grained. But there is a maximum pixel size. So let's say we've got some sort of modulated pattern here. If our pixel size were equal to the peak spacing, Well, the signal on each pixel is just going to be the integral of the intensity across the pixel area. And so if we're just working with 1D pixels, well, the signal here will be the same as the signal there. And we're not learning anything. We're not gathering any information. On the other hand, if the pixel size were half of the peak spacing, so you got a pixel here, a pixel here. Well, this one is seeing the bottom half of the intensity pattern, so it gets a weak signal. This is seeing the top half of the intensity pattern, so it's getting a strong signal, and vice versa. So you're seeing this oscillation. And it turns out that you need the pixel size to be at least half of the feature size that you're trying to resolve. If it's not at least half of the feature size that you're trying to resolve, then you're not going to see it. Now, I just realized I should have put that in the notes, so let me switch to my tablet. Share this screen. All right. There's no guarantee, of course. If I had the same pattern, like this, and I again put my pixels, my pixel size at half of the peak spacing. In this case, of course, here I'm getting the half of the top part, half of the bottom part. Here, so here I'm getting half of the top part and half of the bottom part. Here I'm getting half of the bottom part and half of the top part, half of the top part, half of the bottom part. I'm still, not getting anything. There's no guarantee that a pixel size that's half of the peak spacing will give you information. Things could always go wrong, but there's at least the possibility of things going right. Now let's consider what would happen if I made my pixel spacing somewhere between half of the peak spacing and the full peak spacing. So let me try to draw this. All right, so let's make that pixel spacing a little bit more than half. So it goes a little bit past the bottom. Then this one's going to go even more past the bottom. And then this one is going to go to, well, pretty much the bottom. And then this one's going to go to a little bit past the bottom. So what's happening is that each time it's getting shifted a little bit. The signal here is close to the signal here, but not quite the same, which is close to the signal here, but not quite the same. And then we eventually return to the original, because again, we get from top to, wait a minute, that should have been to there, my bad. And actually, I think I could, well, undo, okay, we'll just, yeah, I'm trying to be fancy, but it's not working. And then this is going to be almost to there. What you see is that the signal is changing from one of these to the next because they're each getting a slightly different sample. And this one should have been, Christ, it should have been to there. Okay. Let's try this one more time. Okay. So it should be to about there, and then it again repeats down to there. anyway, then it starts to repeat. So it repeats every 1, 2, 3. It repeats every 3 pixels. So what happens is that that even though this signal has in reality a periodicity of this, because of the way we're sampling it, we get something with a much longer period. And you actually have seen this in TV and movies. In TV and movies, have you ever noticed, especially on a low resolution TV screen, if someone is wearing a shirt with really fine stripes on it, you get these weird patterns that look kind of like what you'll sometimes see on screen doors? Have you ever seen those patterns, those wavy patterns on screen doors? Well, this is kind of like those wavy patterns on screen doors. The actual periodicity of the screen door is a very fine mesh, probably a couple of millimeters, but you see features much farther apart if you have 2 screen doors almost on top of each other. Those are called moire patterns. You see the same thing on a low resolution TV screen if somebody is wearing a shirt with very fine stripes. You actually see something similar to that in the time domain instead of the spatial domain. If you ever watch on a TV show or movie when a helicopter is flying, the chopper blades look like they're repeating very slowly. That's because if the frequency of the motion was some multiple of 24 spins per second, then, well, if it were exactly 24 spins per second, just like 24 frames per second, then the chopper blade would be frozen in place. And if it's close to 24 rotations per second, or a multiple of 24 rotations per second, then in each frame it's going to be not quite in the same place, but almost the same place, so it's going to rotate more slowly. Anyway, the takeaway lesson from this is that, yes, in principle, you could make a semantic argument that the minimum peak spacing is 0. But if you want to see a feature, first of all, you need non-zero peak spacing. And second, you need pixels that are at least half of that peak spacing in order to be able to see it. This is also called the Nyquist limit, because Nyquist, either a mathematician or electrical engineer, proved that in order to detect a signal at a certain frequency reliably, you need to sample at least twice per cycle of the frequency. Any questions? Anyone? Okay, then let us switch gears. I'm going to switch back to the other device, and I'm going to change the view here, close this one. All right, so a few of you might recognize this from my 2530 class, but the material, we're right now at the stage of the semester where the 2 classes happen to be in sync, much like 2 signals at almost the same frequency. They're going to fall out of sync pretty soon. We're going to talk about diffraction by an aperture. So here's a demo that I can't do from home. Let's say we've got a 1D aperture. We're building up towards the circular aperture. With a 1D aperture, if I shine light through it, well, we get a central peak, just what you'd expect. And then we get these oscillating but decaying side lobes. All right, and these decaying side lobes require a wave theory of light. And their spacing turns out to be proportional to the wavelength, because if we redo the experiment with red light instead of green light, then we get a larger spacing between the side lobes. Also, if we do it with apertures of different sizes, and I'm pretty sure that the people who made this meant for these aperture sizes to be in millimeters, not nanometers, then very small apertures, sorry, very large apertures lead to very small side lobe spacing. Intermediate size apertures lead to somewhat larger side lobe spacing, and then very small apertures lead to side lobe spacing where here's the first peak, and then way over here you can just barely see the second peak. It's pretty far off. So we've got a spot spacing or a side lobe spacing that's inversely proportional to the slit width. And that's what we want to try to understand today. So here's our geometry. All right, we're going to consider a slit going from y equals minus a over 2 to y equals plus a over 2. And we're going to add up fields from every point along here. All right, and we're going to measure all of the distances with reference to the center. So we're going to say that the distance from the center of our aperture to whatever point we're currently trying to detect light at over here, that distance is R0. And if that distance is R0, then this distance will be R0 plus delta R, and delta R up here will be negative, and delta R down here will be positive, because up here, this point is closer to the point on the detector. So if it's shorter, then delta R must be negative. We'll call this theta. And again, we treat these two paths as almost parallel, which means that this line is perpendicular to both. So we've got theta here. This little angle down here is 90 minus theta, which means this angle up here is theta. Delta R is opposite theta. Y is the hypotenuse. So delta R is, and there should be a minus sign there, y sine theta, or minus y sine theta, but we correct it over here. And then we're also going to need to work out R, because the electric field from each point is e to the IKR over R, right? And we know that this distance, which is fixed, L, the horizontal distance from screen or aperture to detector, that distance is R0 cosine theta. So R0 is L over cosine theta. And then 1 over R, if we go over here, must be cosine theta over L here and here. So when we set up our integral, our e to the IKR becomes e to the IK R0 minus IKY sine theta. And then we have to do a u substitution to do that integral. It looks like a messy integral, but that's really just because we've got e to the y times a bunch of constants. But that's the same as doing the integral of e to the y times one constant. It's just that we wrote our constant as something much messier. All right, so we do our u substitution. We still got our cosine theta over L. We get 1 over the constant. Whenever you integrate e to the constant times y, you get 1 over that constant times e to the constant times y. So we get all that over here. And then we've got the difference of two complex exponentials. We're going to multiply top and bottom by minus a over 2. And we're left with e to the I ka sine theta over 2 minus e to the minus all of that. And then we divide by, well, 2i here and ka over 2 sine theta. And when we do that, we've now got e to the something, e to the I something minus e to the minus I something over that something and over 2i. So we've got sine of ka over 2 sine theta divided by ka over 2 sine theta. And a lot of people get uncomfortable with that because it's a mess of expressions. You've got the sine of a sine, and so people try to take all sorts of shortcuts. You can't take any shortcuts with it. You just have to first multiply sine theta. Then you multiply by ka over 2. Then you take the sine of all that. Then you divide by Ka over 2 sine theta. Now this is a new function. It's called the Sinc function. And it's similar to something that you learned the limit of in calculus, but in calculus, the only real interest in that was proving, at least in freshman calculus, the only real purpose of that was to prove that its limit as x goes to 0 is just 1, so that you could get formulas for derivatives of trig functions. But it shows up all the time in signal processing, and since I just talked about pixelation, it's worth saying a little more about that. A digital signal is just zeros and ones. So either your light intensity or your voltage or whatever is 0, or it's 1. Off, on. Well, people want to take these square waves and break them up into sinusoidal waves, partly because it makes the math easier, and partly because any real signal is, if it's an optical signal, it's just going to be a bunch of different light frequencies all mixed together, and each light frequency is its own sinusoidal wave. And when you do that integral, if you go through all the steps, you wind up getting sine of omega delta t over 2 divided by omega delta t over 2. And so that's called the sinc of omega delta t over 2. And here is a graph of it. All right, so this shows up all the time in digital signal processing. And if you work in the optics industry, depending on what you're doing, if at any point you're converting your signals to digital form, or you're doing anything with interference or holography or phase masks, then you will probably have to learn some of that at some point. Any questions? Okay. So we've got the form for the electric field. Now the intensity is proportional to E star E. So we're going to get cos squared theta, square the constants out front, and sinc squared. We're going to get something that looks like this, which is not too different from the patterns that we've seen in Zemax when we look at a diffraction limited lens. There are some details that are different, but you can get a long way. This is actually, it's qualitatively very similar. That's why we're spending today on this. This is 0 if the input to the sinc function is 0. And the input to the sinc function was K over 2 sine theta. So K over 2 sine theta has got to be pi or 2 pi or 3 pi or 4 pi, etc. So that means the sine of theta times K over 2 is pi times an integer. All right, well, Ka over 2 is going to be 2 pi times A over 2 lambda. So we're going to get the 2's cancel, pi A over lambda, sine theta equals pi times a constant. In the end, sine theta is an integer times the wavelength over the slit width. All right, that's exactly like what we saw a few slides earlier, where we found that this width here was proportional to the wavelength, goes up as the wavelength goes up, and inversely proportional to the slit size, meaning that as the slits go from large to small, the diffraction pattern goes from small to large. So let's switch to Mathematica. I have posted these Mathematica files on Blackboard if you want to follow along at home. All right, diffraction pattern of one slit. So I've defined a function here that calculates the intensity profile. And we fix the wavelength. I've chosen 0.7 microns for now. And as we increase the slit size, you see that indeed the function gets narrower, right? So
Sir, you
let's,
said the diffraction is proportional to E star E. Do you mean the intensity is proportional to
yes,
E star E?
the intensity, yeah, the intensity, the thing that we actually detect is proportional.
Okay, thank you.
Sorry, no problem. All right. Somebody's playing the radio for us. Okay. Yeah, that happens. Anyway, so here we've got a diffraction pattern, and let's make it so that the aperture size is 2, or very, very close to it. All right. Now we get, when the aperture size is about 2, we get that the first node, the first minimum, is around 20 degrees on either side. Now I'm going to cut that in half. So instead of working in the near infrared, we're going to work in the near ultraviolet. And we're going to, again, take this up to about 2. And now that first peak shows up not at 20 degrees, but around 10 degrees. And this is all approximate. I haven't zoomed in. But what I want you to take away is that indeed, this diffraction pattern has its central width proportional to the wavelength and inversely proportional to the aperture size. Any questions? Okay. And you can ask why these effects aren't visible in daily life. Well, the first 0, sine theta, is lambda over A. Middle of the visible spectrum, more or less, 5 times 10 to the minus 7 meters. It's hard to make features reliably by hand under easy circumstances that are any smaller than about a millimeter. So we would see these features when the sine of theta is less than 10 to the minus 3, or theta is 0.03 degrees. That's really tiny. We can also do a square aperture. And with the square aperture, we need to do a little more trigonometry. So let's set some things up. The distance from the center of our aperture to the center of our detector will be L. But we're not always finding the contribution of something at the center to the field at a point B off axis. We're going to be going from point A to point B. So we'll say that R is the distance from the center of the aperture to point B, big R, and then little r is the distance from point A to point B. Little r will be big R plus delta R. And big R, if we just use the Pythagorean theorem, is the square root of L squared plus big X squared plus big Y squared, where big X and big Y are the coordinates in our detector plane, and little x and little y are the coordinates in our object plane, or our aperture plane. And by the same logic, using the Pythagorean theorem in 3D, little r will be L squared, square root of L squared plus big X minus little x squared, because that's going to be how far this way laterally we have to go to get from big X to little x, and big Y minus little y squared, because that'll be the difference between how much further up we have to go when we go from point A to point B. And in anticipating that certain things are going to be small, we are going to preemptively factor out some L's. L is going to be much larger than any of these other coordinates. So we can factor L squared out of everything in here. And then since that L squared is still under a square root sign, turn it into an L when we take it outside the square root sign. We're going to get this for big R, this for little r. And then we start making approximations. We can't get rid of everything. If we just got rid of everything that's small, we'd be left with big R equals little r equals L, which is, well, maybe to within 10% accuracy, but it's not only kind of inaccurate, it's not telling us how these other things matter at all. But if we just keep all the terms, then we have something that's intractable. So we're playing for a middle ground here. And you might think, well, that's being kind of fast and loose. Well, the thing is that if you're going for a middle ground, you don't just get to pick and choose terms. You have to go and say, okay, first we keep the absolute largest, then we keep the next largest, and then we keep the next largest after that. So the largest terms are going to be big X squared and big Y squared. So we have to keep those if we're going to keep anything. Then the next largest will be little x times big X and little y times big Y. Those are larger than little x squared and larger than little y squared, for the same reason that 0.1 is bigger than 0.1 squared, and 0.1 times 0.5 is also bigger than 0.1 squared, because 0.1 times 0.5 is 0.1 times something bigger than 0.1, whereas 0.1 squared is just 0.1 times itself. All right, so we get this, and this is supposed to be a -2 over here. And we're going to, again, make those assumptions. We're going to use a Taylor series. We're going to assume that all of this stuff here is much less than 1. So we can use the Taylor series for 1 plus alpha to the n when alpha is small. 1 plus alpha to the n is 1 plus alpha n. And if we're taking a square root, n is 1/2. And then alpha will be either big X squared plus big Y squared, or all of that -2 times these terms. So little r is going to be this mess. Big R is going to be this slightly less messy thing, but still complicated. But here's the most important thing. Everything that's in big R is in little r. So little r is big R minus all of this stuff. So we take L times 1/2, L times 1/2, times all of this stuff over L squared. And there's a 2 in front of each of these terms. Those 2's cancel out the 1/2. There's an L over L squared. So we're left with something pretty simple. R minus little x times big X over L minus little y times big Y over L, right? Which is somewhat complicated, but not nearly as complicated as what we had before. And it involves things that we can interpret. Okay, let's say that our K vector is going from the aperture to a point in the detector plane, because by definition, wherever we're looking in the detector plane, we are just picking up light from waves that traveled in a direction that will take them from the aperture to the detector plane. All right, so K is going in the same direction as R. All right, KZ is the component to the right, KX is the component into the page, like this, and KY is the vertical component. So KX over K, because these two vectors are parallel to each other, the X component of K over the length of K is the same as big X, one of the components of the R vector, over L. And you might say at that point, well, L isn't quite the length of the R vector. I agree. L isn't quite the length of the R vector, but it's close. And if we were to do this more precisely, it turns out that what we would get is that we would get that 1 over R is 1 over L times 1 plus delta R over L. And that is roughly, I should have done this, 1 over L minus delta R over L. You know what? I'm going to do it on my tablet. Let's share that screen. Share that screen. Go into OneNote. All right. 1 over R, we could rewrite this as 1 over L plus R minus L, or 1 over L times 1 minus R minus L over L. And now here's the crucial point. This is tiny, right? And so we can rewrite that as 1 over L times 1 minus R minus L over L to the negative 1 power, right? So now we've got 1 minus a tiny thing to the negative 1 power. And remember, if we call all of this alpha, and this is n, 1 plus alpha to the n is roughly 1 plus n alpha. So we're going to get 1 over L times 1 plus negative 1 times negative R minus L over L. All right? This becomes plus 1. So we are getting 1 over L plus R minus L over L squared, right? So we're going to have 1 over L plus something over L squared, something tiny divided by a big number. All right? And if we switch back to the other notes, then what we would be left with over here is just big Y times something tiny. It would all go away. So the end result is this. We can write it as the product of, we can write it as the integrand as the product of e to the minus I, x component of k times x, e to the minus I, y component of k times y. And then because of the way that this integral was set up, we can actually factor that because this integrand, because we're integrating over a square domain, we can write it like this. We get the product of two sinc functions. And let's switch to another Mathematica file. So let me go to the diffraction pattern of, oh wait, it was the diffraction pattern of one slit. It was just further down in that file. So what I've got here is I've got a function that calculates the diffraction pattern of a rectangle. It just multiplies those sinc functions. And we fix the height of the rectangle and we vary the width of the rectangle. So the height of the rectangle, I've set this up so that the height is 2 microns. The wavelength is about half a micron. And when the rectangle is very wide, our diffraction pattern is mostly vertical. When the rectangle is very narrow compared to the height, our diffraction pattern is mostly horizontal. And this is something that we're going to see over and over again with diffraction patterns. Tiny objects make wide diffraction patterns. Large objects make small diffraction patterns. And when our object is tiny in one direction, say horizontally, and large in another direction, say vertically, then we get the inverse. We get something that is large in one direction, say horizontal, and tiny in the other, vertical. All right, so in general, these diffraction patterns are kind of the inverse of the structure we're looking at. We've already seen this on the assignment you did today, where you found that if we worked with a very narrow lens, made the lens aperture very small, the light spread out over a large area. Whereas if we made the lens very wide, but not so wide that we get aberrations, just wider than it was before, but still not in the aberration case, then we get a spot that is fairly small. And we're going to talk on Thursday about how we get a diffraction pattern out of that, how we relate the image formed by a lens to a diffraction pattern. But it's just a general lesson of wave optics that the larger an object, the less that waves spread out when they interact with it. And the smaller an object, the more waves spread out when they interact with it. This is why people who do diffraction for a living in the field called X-ray crystallography talk about reciprocal space and reciprocal lattices, reciprocal vectors even. They're not literally putting a vector in the denominator of an expression, but they're working in cases where the more things spread out, the smaller the object actually is, and vice versa. So they talk about reciprocal space all the time. Any questions at this point?
Yeah, where would you use a rectangular aperture?
So a place where people would use rectangular apertures is in something called spatial light modulators. The idea of a spatial light modulator is what they would basically do. They have pixels. They usually do them nowadays as mirrors. There's two ways they could do it. They can either use electro-optic effects to change the refractive index of each pixel. What that means from a side view is that you get a phase shift. If I were to compare this wave versus this wave to travel the distance d in air, the number of cycles is going to be d over lambda. Whereas this wave that traveled d through something with index n, the number of cycles will be d over lambda over n, the wavelength in there. Or
I'm not seeing any.
Oh, right, I didn't share the screen. My bad. Let me do that now. Share my other device. Okay. So what they do is they work with an array of pixels, and in a transmission geometry, each of these pixels will be made of some material whose refractive index changes when you apply a voltage to it. So if they were to travel a distance d through air, or even d through something with, then we've got light traveling the same distance through something with an index n2. All right, so the number of cycles here is d over lambda over n2, or n2d over lambda. Then on each of these pixels, you get a different phase shift. And so by applying a voltage, I can make this phase shift whatever I want, because I can shift the value of n here, all right? And I can shift the value of n there. So I can give each of these different phase shifts. And then what I get on some distant detector is the sum of the diffraction pattern of this, and the diffraction pattern of that, and the diffraction pattern of that, and so forth. Okay? And people are doing more and more things with these spatial light modulators. The other thing you can do is that if these pixels were not transmissive but reflective, then we could if we had, say, some detector that they were reflecting off of like this, well, if one of them is raised really high, then the light bouncing off of that travels a different distance than the light reflected off of this one, which is raised up much less. All right, this one is going to travel a longer distance, have a longer phase shift. And so when we add up these two pixels, we're adding up the diffraction pattern of a square or rectangular aperture that's at this distance and a square or rectangular aperture that's at a slightly different distance. Now, what do they use that for? Well, one thing you could do is you could just use it to shape light into literally anything you want, because if you control the phase of light, you can control how it will interfere. You could control the patterns made. You could do holography. You could do laser light shows. But there are much more practical things. Many of you might have heard of something called adaptive optics. And adaptive optics is a way of correcting for aberrations. It has nothing to do with your lenses. It has to do with the fact that everything we've done with lenses has been based on the assumption that the lens might have the wrong shape, but at least the light reaching the lens was all going in a straight line. Okay? All of the light was going in straight lines before it hit the lens. But what if the light was traveling through the atmosphere? And so maybe it was still going in straight lines, maybe it wasn't, but if the air here has a different index than the air over here, then they've got in different phase shifts traveling through the atmosphere, okay? Because of perturbations in the density of the atmosphere, perturbations of the temperature of the atmosphere, and so these waves have gotten different phase shifts. So we can no longer assume that when the light hits the top surface of the lens, it's at a constant phase, all right? The light has already undergone a bunch of different phase shifts along different paths. And because it's undergone different phase shifts along different paths, we don't have constant phase. We don't have constant time. Everything we did with the principle of least time, we started off assuming that along this leg of the journey, everything had taken the same time. Now they've all taken different times. They've all gone different phase shifts. These spatial light modulators correct for that. That's what adaptive optics is. People have ways to figure out what were these phase shifts by imaging something where, okay, we know what we would be seeing if the light all had constant phase, if all the light had the same phase when it hit here, if everything reached here at the same point in the cycle, taking the same amount of time. So we look at something whose picture we know what it ought to look like when it's ideal, but then of course it's not ideal. So based on this bad picture, we figure out what the phase shifts would be. This one got a different phase shift than that one. So we put our spatial light modulator there, and we apply a phase shift, either in transmission mode, or maybe they do it in reflection mode. And then you go to your lens or mirror. All right. So spatial light modulators are used for that. So they're used in telescopes all the time. People like to think that spatial light, that the adaptive optics was designed for astronomy, but I have heard stories of how the Air Force came up with certain adaptive optics tools for satellite tracking and didn't tell the astronomy community about it. The Air Force came up with it so that they could track Soviet satellites with high accuracy, or let's be honest, do a lot more than track, actually take pictures from the ground, get details of what's going on in the satellite. And then sometime later, astronomers independently invented some of these techniques for looking at the center of the galaxy. So they're used for that. But nowadays, people have realized that, hey, we don't just have to use spatial light modulators and adaptive optics to look at the sky. We could also use these things to look through tissue, right? Because if we've got a specimen of tissue, tissue is very inhomogeneous. We know this because we aren't transparent. If we were transparent, medicine, at least some aspects of medicine, would be somewhat easier. But we aren't transparent. Our tissue is highly heterogeneous. Even the cells themselves are highly heterogeneous. That's the only reason why we can see cells at all under a microscope. So the light goes and it's getting refracted and changing paths as it goes through. And so nowadays, people are using spatial light modulators to work to correct for that and essentially see through skin. All right, and a lot of this work is still in its early phases. I've avoided talking about it because I know the basic concept, but I've never done anything with it, so I can't give you all the details of spatial light modulators, but maybe I should in some future year redesign the class around that. They've had some luck in looking through skin, but a lot of the time, they're just happy if they could look through the first few layers of the brain. Because right now, using infrared light, they can see 0.5 millimeter into a mouse brain. 0.5 millimeter is nothing on the human brain, which is several centimeters thick, maybe tens of centimeters thick. But on a mouse brain, 0.5 millimeter is a substantial fraction of the outer layer. That's a lot of brain that you're looking at. And as much as there are differences between mice and men, there are also some similarities between mice and men. They're both mammals. Not only mammals, they're placental mammals, so they have fairly recent common ancestors. And there are enough similarities that just being able to look a few millimeters into a mouse brain would tell you a tremendous amount. And so people are using adaptive optics and spatial light modulators for that. But all of this comes down to using the diffraction pattern of a square or rectangular aperture, either in transmission or reflection mode. I know that was a bit of an aside, but it's really cool stuff. It would be well worth learning about. I'm teaching you enough wave optics so that when they start talking about interference and modulation and these things, you'll be able to understand them. But if you really want to learn about spatial light modulators, you should talk to someone who's used them. But I'm just here to give you enough on the concept so that once someone says, oh, okay, well, it's coming in with this phase and it's doing that, you'll understand that part. And then they can tell you the tricks of how they actually use that information. Questions? One underappreciated thing about science is just how much of a debt biomedical optics owes to astronomy. I personally prefer studying the physics of tangible things at ground level rather than very distant objects. That's my own personal preference, but there's no denying that astronomy has done huge things for all of science in terms of imaging science and remote sensing. In the field that I've done the most work in, a lot of the early algorithms for analyzing these high-resolution microscope images were taken from astronomy. And even to this day, that continues. Spatial light modulators, which I just said I know less about, but I know enough to know that all of that came from astronomy. Remember the Event Horizon Telescope where they imaged a black hole at the center of the galaxy a year ago? I frankly expect that the biggest significance of that work will be the absolutely incredible tricks that they used to stitch together all of this phase information and sort out signal from noise. I mean, I'm not trying to be dismissive of the significance of general relativity. It's the basis for GPS. But beyond the fundamental significance of it, I guarantee you that some of the techniques from that will be taken directly to biomedical imaging. As a matter of fact, I know that a lot of the people on that project weren't even really astrophysicists. And I say that not in some dismissive way, but rather to make the point that if you look at their expertise and training, yes, they all learned some stuff about black holes while doing this. But if you look at what their previous training and experience were, and a lot of them are computer scientists and applied mathematicians working on image processing. And people like that, they can learn about black holes just as they can learn about biomedical optics, or they can learn about earthquakes if they were to start doing seismology. They can learn about the details of whatever system they're studying, but their true expertise is in the math and technology behind the imaging. And I know for a fact that some of those people work on more than just black holes. And a lot of the techniques they developed for really rising to that extreme challenge of synthesizing all of this data from black holes will be immediately applied to other problems, because they have jobs where they only spend part of their time on black holes and part of their time on other problems. And so astronomy and the space program are kind of an extreme environment. They're at the limits of what we can do, because you're studying something so far away, and frequently you're sending things into space, which is an extreme environment, and all of that stuff later gets applied elsewhere. All right, I've gone pretty far afield. I want to just say a little bit more about interference and diffraction. So let's close this one. Let's go to some other notes. I want to say a little bit about diffraction by two finite slits. So let's go back to Young's two-slit experiment. In Young's two-slit experiment, we saw all of these evenly spaced bright spots, but you notice how first they get dimmer, then they get really dim, then they start to grow again. That wasn't in any of what we did before. Okay, we got the evenly spaced bright spots because we got a prediction of an interference pattern. It would be something like 1 plus cosine of k delta r. And we got some of the decay from the fact that, well, this is something up here is farther from the slits than something in the center. So of course we would expect it to go dimmer as we get out there. But the fact that it gets dimmer and then brighter again, that part wasn't expected. So let's try to understand that. And I just realized I opened the file that doesn't have the second part. So let me pull up the file that has the second part. All right, so we've seen our prediction for the interference pattern of two tiny slits, or one finite slit. Now let's combine them. We've got two different slits, and we're combining paths from all along here and all along here, and they meet at infinity. And we're working in a coordinate system where y equals 0 at the center. But let's break that up, because here's y equals d over 2. This is a over 2 above that, a over 2 below that. Here's y equals minus d over 2, a over 2 above that, a over 2 below that. We're adding up these two integrals, which look just like the integral we did a little while ago earlier today. But let's make some substitutions. Let's say that in the top slit, y equals d over 2, the center coordinate, plus delta y1. And in the bottom slit, y equals minus d over 2, the center coordinate, plus delta y2. And so then we can rewrite all of these exponentials as products of, here's something that has the center coordinate, d over 2 or minus d over 2, and then our ik sine theta, and something that has delta y in it. And when we do that, well, this part doesn't depend on y, and this part doesn't depend on y, so each of these factors can be pulled outside of the integral, and this factor can be pulled outside the integral. And we're left with two integrals where, okay, delta y has different subscripts on them, but delta y is multiplied by the exact same things in the exponent, and the range of integration is the same in each case. These are the same integrals. And so we've got that our electric field is just this integral multiplied by the sum of these factors. And the sum of these factors is cosine kd over 2 sine theta. And this is a sinc function. And if we go into Mathematica again, and this time we pull up the diffraction pattern of two slits. Now we fix, this is, that's two narrow slits, sorry. Let's look at two finite slits. All right, we can play with theta max, the range of angles that we look at. We can play with D, the spacing between the slits. And we can play with A, the single slit width. And what you should notice is that when I play with D, if I make D small, these closely spaced spikes, if I make it really small, the spikes are still closely spaced, but not as closely spaced. And when I make D large, the spikes become much more closely spaced. When I play with A, if I make A small, well, if I make A really small, we don't even see a secondary bump here. If I make A somewhat larger, we can see a secondary bump. If I make A larger still, we can see a third bump in the beginnings of a fourth bump there. Make A really big. So you can see the central peak, secondary bump, the third, the fourth. And if you really squint at it hard enough, you could persuade yourself that there's a fifth out there if you want. All right, and so what I want you to take away here is, first of all, that the diffraction pattern we get is going to be a sinc function multiplied by something that depends on the spacing between the slits. And the spacing between the slits doesn't affect the really large features, the things that are the position of the second and third bump. The spacing between the slits just affects the really fine features. And that's because the slits are really far apart. If the slits are really far apart, once you do a diffraction pattern, things that are really far apart on the actual object result in features that are really close together in the diffraction pattern, and vice versa. Whereas here, the smaller feature is the size of the slits, because the slits are smaller than the spacing between them. That really small feature on the object affects the really big features on the diffraction pattern. Questions?
Could you go to the equation on the other paper just so I can finish looking at that and copying it down real quick? Thank you.
Yeah, and don't worry, I'm going to post this lecture, so you don't have to keep any of this copied. I'm not sure which page, maybe here?
That one, precisely.
All right. And I'm going to post all of this, so you won't have to hang on to any of it.
Is there any benefit to looking at slits that aren't symmetric, or is it just like adding unnecessary complication?
What isn't symmetric?
The slits, like if you had two different sized slits.
Oh, if I had two different size slits, then I couldn't do this factorization anymore. But even though, in general, we can't assume symmetry, in the practical application of a spatial light modulator, we totally can do that. Because in a spatial light modulator, we have, you know, a whole bunch of identical pixels just at different positions, and each pixel introduces a different phase shift. So what you would essentially get is you get that product of sinc functions from each individual pixels multiplied by the phase shifts of each of the pixels. You know, whereas in this case, the phase shifts come from the pixels being at different locations. In the spatial light modulator, the phase shifts would come from a combination of being at different locations and also giving different delays either due to their height or their refractive index. Now this is often, okay, so this larger scale feature is often called an envelope function. And we could do something more general. We could have a whole bunch of different slits. We don't need to assume that they are evenly spaced. They could be at whatever height we want. But again, each one would give a sinc function if they're all the same width. If they're different widths, all bets are off. But in a key important application, they're all at the same, they're all of the same width. And then we would have these phase shifts due to their positions and possibly other factors. So you just have the product of a sinc function and something due to their positions. In X-ray crystallography, this gets called the form factor. Basically, that's telling you how strongly individual atoms of the crystal are scattering X-rays. And this gets called the structure factor, which tells you how the atoms are arranged. Let's say we had 3 slits. That's a common enough thing. Nowadays, in quantum optics, it's kind of a big deal to do 3-slit experiments. Everybody knows how to calculate the classical diffraction pattern of 3 slits, but there are some people who have worked on quantum effects in the 3-slit experiment. And so there, you would have the sinc multiplied by e to the I k times the coordinate of each slit, either minus d, 0, or plus d. Now what if we had 3 very tiny slits? Can anybody guess for me what we would get in that case?
Just the sinc function?
Really? We get 3 very tiny slits? The spacings don't change. If the slits are very tiny, which variable goes to 0, A or D?
A, sorry.
All right, and what's sinc of 0?
0.
What?
It's not 0, because it would be sine of 0 over 0.
And what's sine of 0 over 0?
Undefined. Indeterminate.
Okay, yes, it depends on how we take that limit. But in calculus, what did you learn was the, oops, why can't I pull up my, I'm trying to get at something in Zoom, okay. In calculus, somebody's posting in the group chat. Remember that in calculus, if we took the limit a certain way, sine x over x goes to 1 as x goes to 0. And so in that case, this would just be 1 and you would be left with this. Another example, if we had a phase mask here, like in the case of the spatial light modulator, then we would still have everything we had before. We'd get a sinc from each one, but this top one would get an additional phase shift, e to the I phi, where e to the I phi would depend on how much the light got delayed in here. And again, that's what people do to shape light beams. Last example, the 4-slit experiment. If we had 4 slits, then we would just add up e to the I k. Here we'd have coordinates d over 2 and 3d over 2. So we would get e to the I kd over 2 sine theta and e to the minus I kd over 2 sine theta. That gives you a factor of 2 cosine kd over 2 sine theta. And here we have e to the plus or minus 3 I kd sine theta all over 2. And that would give you the cosine of that. Any questions on what I went over?
I have one. So as far as notations go, each one of these sine thetas that you have, as far as the positions of the slits go, each one of those thetas should be a different value, right? It's the angle from that slit to whatever point we're looking at.
True, except we're making the approximation that the detector is so far away that all of these paths meet at infinity.
Okay, so we essentially consider them to be like almost right on top of each other as far as theta goes.
Yeah, let me go back to a diagram. So basically what you'd be assuming is that in reality, all of these slits would be more like that. And our detector would be over here. And so this would be one of the paths. And this would be the other path. It would be like that, so close to parallel that these are the same theta. You know, I'm doing in order to set up the integrals and do the geometry, I have to do very exaggerated things like this, where there's no way that any reasonable person could say these two thetas are the same. This is clearly different. Oh, and I'm not, yeah, okay, I'm sharing. These two thetas are clearly different. But in the uppercase that I'm doing, you know, if I had drawn these with a ruler, here, let's do that. All right, I will try doing that with a ruler right now. Those two paths, I mean, yes, there is a slight difference between them, but it is very small.
Okay, thank you.
You're welcome. Other questions? All right, then let's switch gears. Let's go into Zemax. If you look on Blackboard, I have posted the next assignment. And with the next computer assignment, and by the way, I apologize for the fact that these things are all in some random order. I cannot figure out how Blackboard arranges these things. I keep trying to reshuffle them into some sort of numerical order, and then Blackboard unshuffles them for me. It's fine when I'm posting documents. If I post something as a document with no submission link for you, I can put them into any order I want, and I've been doing that for years to try to get them into some sort of reasonable order. But for reasons beyond my comprehension, Blackboard does not allow me to shuffle assignments with submission links. Anyway, you're going to see two Zemax files there. The ZMX file is the one that has all the specs, and then the ZDA file is the one that you need so that it will show all of the analysis the way I've done it. So go ahead and download those Zemax files if you're in front of a computer with Zemax on it. I just upgraded Zemax, and now it's all ready. How many times in a semester can they upgrade Zemax for me? All right, I'll give everybody another minute to do that. I'm gonna get a drink of water. All right. If you still need another minute to download that, I'm just going to open it. I'm just going to tell you a little bit about where I got it. I got it from this website. And the person who runs this website claims that all of these files on here are US patent numbers. I Googled some of these patent numbers, and I'm not necessarily finding them. So I can't vouch for who designed these originally. I can't promise that these are the most modern designs. What I can say is that I have tried to contact microscope manufacturers and say, hey, would you be willing to share a Zemax file with me for educational purposes? And the answer is always no. At best, they'll share black box files with you where you don't see all of the details. Anything proprietary is hidden. It's encrypted so that it's encrypted, and Zemax will decrypt it for its own use so they can do the calculations, but it won't share the results of the decryption. It will only share the results of the ray trace. So I can't vouch for the source of these. These may not be the most modern designs. What I can say is that it's a pretty good design. We're going to verify that in a moment when we start looking at spot diagrams and whatnot. But in the meantime, let's just look at this diagram. This is an infinity corrected objective. And what that means is that we are taking light that goes in a bunch of rays from infinity going parallel to each other and sending them in. And we're doing this in reverse order. In reality, this is where the object would be in a real microscope. But we're taking what the object would be in a real microscope, and we're putting it in the image part of Zemax. And where the image would go to infinity. We're putting the object. There's a few reasons why people do that in Zemax. For one, doing quick focus so that it automatically adjusts the last layer thickness, the distance from the very last lens to where the image forms. That's easier than doing quick adjust. So it's just to make things a little bit lazy for the user. Also, when people talk about microscope images, yes, in reality, the image is something magnified. So in reality, something that's 10 microns on the object could be 100 times that, or 1 millimeter in the image. But nobody in real life says, okay, now if you look 1 millimeter away, of course, they just say if you look 10 microns above this point, or this thing is 10 microns across is how they say it. Nobody ever says, okay, in the image this is a millimeter across, but really it's 10 microns. They just say this is 10 microns across. So putting the object in the image plane helps you talk about what's going on here in the ways that people would talk about the actual microscope image. But remember what we said a few weeks ago when we were reading that paper. We said that in a real microscope, if you've got an infinity corrected objective, then what happens is, again, let me go to OneNote. All right, it is not letting me, okay, now it gave me more space. What's happening is here you've got your objective lens, here you've got your object, Your objective lens sends the rays parallel to each other. And so here's y. Here's the distance from the focal point to the object in the focal plane. Then those rays will go at an angle theta, given by y equals f objective tan theta. And then those rays hit a tube lens. And what happens when rays making an angle theta hit the tube lens? They're all parallel to each other. If rays going parallel to each other hit the tube lens, come on, what do they have to do?
They have to
Get focused at the same point.
Yep, they're all going to go to the same point, and that will be at a distance y2, if this is y1. y2 will be f tube tan theta. So tan theta is y1 over the objective focal length. It's also y2 over the tube focal length. So y2 over y1 is equal to f tube over f objective. So in this Zemax file, we can't actually look at this and say what the magnification is, because right now there is no magnification, there's no tube lens. All we've got is something that is taking an off-axis object and hopefully making the rays go more or less parallel to each other, or vice versa, taking off-axis rays and hopefully bringing them more or less to a point. Any questions on how that works? On
So
that
this whole
concept?
setup that we have in this file is the entire objective, and we send the parallel rays on the left into the tube lens.
No, we're going to eventually add a tube lens. One of your tasks on the assignment, first we're going to characterize this lens without the tube lens. Then what you're going to do is you're going to put a tube lens over here on the left. And you're going to add in the tube lens, and you're going to put objects to the left of that. And so an object here will send rays through the tube lens. The tube lens will then collimate them. So if we had an on-axis object here, the rays will go into the tube lens that you're going to put here, and then they'll go parallel and they'll get focused to the center over here. And if you had an off-axis object over here, then the tube lens will send those off-axis rays, the rays from that off-axis object at an angle here. And then the rays going and making that angle will eventually get focused up here. But initially, we're not going to do that. Initially, the first part of your assignment is just going to be to characterize this. One other thing about this. On the assignment you just turned in today, you probably found that the performance was pretty lousy past a numerical aperture of somewhere around 0.05, 0.08, something like that. Does that sound about right?
Yeah.
Yeah. Okay, well, this thing has a much larger numerical aperture, meaning that this thing can gather rays over a very large range of angles and still produce excellent images. And I want to talk a little bit about how it does that. First, you see how this surface here is concave. What that means is that you can bring the object very, very close to the lens. If we had a convex surface here, it would be very different. The rays would be hitting the surface at huge angles if this were convex. I mean, this ray here, if I made this last surface convex, this ray would be hitting at a huge angle. But because it's concave, this ray is hitting the surface not head on, but at a fairly reasonable angle. And then it slowly bends it. And then if we zoom out, it's gotten bent somewhat. It gets bent a little more. It gets bent a little more. There's this whole process of gradual bending of the rays. Okay. Another thing you should notice is that, all right, we've got that concave lens doing its thing. These three lenses here, this one, and this one, they're not exactly the same as each other, but they're very similar to each other. And I've had you on multiple assignments now say, hey, what if we put 2 or 3 plano-convex lenses in a row? These aren't quite plano-convex, but in general, they have one surface that's much flatter than the other surface. This one is slightly concave. This is very bulging. These are not so different from plano-convex lenses. One other big difference, of course, is that these are made out of 2 glasses. Why would they use 2 different types of glass? Think about the lenses we studied in that paper we read. Why did they make all of those lenses out of at least 2 different kinds of glass?
Well, because when Snell's law is like n sine theta, right? So if you change n, you don't have to change theta as much.
No, not really. There is the fact that if you have a doublet, of course, you get 3 surfaces instead of 2. That gives you more degrees of freedom to play with. And you get a smaller delta n. That's part of it. But what was the other big thing for using more than one kind of glass?
You can have different wavelengths you can snatch.
Yep, you take advantage of the fact that even though the refractive index changes when the wavelength changes, the refractive indices of different glasses change in different ways when the wavelength changes. So these changes kind of compensate out and you get the same focal length, the same performance for different wavelengths. But if we leave that aside, you know, if we were only working with one wavelength, this is not so different from having several plano-convex lenses in a row. Of course, it's more sophisticated. But what I'm trying to convey here is that the lens systems I've been having you study are simplified versions of things that actually work in some realistic designs. So if you can get the idea of why 2 or 3 plano-convex lenses in a row are good, then it's not a huge leap to understand why 2 or 3 doublets that are almost plano-convex are also good. The doublet part being, of course, just that, hey, now we've got 2 kinds of glass. We can compensate changes in refractive index and work well at more than one wavelength. The almost doublet part, well, that just comes from the fact that plano-convex is cheaper to manufacture, but having a little bit of bending at this surface is also good. All right. So let's look at the performance of this thing. In order to look at the performance, what's the first thing you'd probably want to look at?
Spot diagrams.
And then in order to see if these spot diagrams are any good, let's show the Airy disk. Oh, this on-axis performance is beautiful. Almost all of the rays are within the Airy disk. And the average distance the ray goes from the center is well below the Airy radius. This one, yeah, it's worse, but that's pretty far off axis, okay? It's pretty far off axis. Now that's still just in ray optics. Let's take a look at the PSF cross-section. All right, well, that's choppy. So let's always normalize it so that the peak is 1. It makes things easier to interpret. Let's go from 32 by 32 to 128 by 128. Okay, that looks a lot like the pattern we got earlier today. There are some quantitative differences, but qualitatively it looks awfully close. Then let's do diffraction and closed energy. And the thing you should notice is that while none of these patterns exactly match the diffraction limited prediction, they get pretty close, all right? They are very close. And they only really differ far out in the tails. If you look at where half of the energy goes, here's the diffraction limit, here's the on-axis, here's the off-axis. So your task in the first part of the upcoming assignment will be to, well, basically look at that graph and then see how much farther could you move things off-axis, and how much further could you move things off-axis before the spot size doubles. And like here, if we go to 6 degrees off, well, 0 degrees or on axis, you get 50% of the energy at a radius of 0.258 microns. 6 degrees off axis, the spot size is now 0.34. 7 degrees off axis, okay, now we're in the aberration limited regime. So somewhere between 6 and 7 degrees off axis, the spot size doubles. And then once we go any further than that, the spot size starts to increase drastically as we go off axis. And once the spot size changes drastically as we go off axis, that means we're in the aberration limited regime. And if we look at the spot diagram, yeah, we see some absolutely horrible aberrations there. But on the other hand, if we were only 3 degrees off axis, all right, we're seeing a little bit of coma here, but the vast majority of the light is within that airy disk. Any questions?
I have one actually. So just real quick, in the actual physical layout of that lens,
Yeah.
you said we were going to add a tube lens later. So this entire collection of lenses that we're looking at, that's the objective lens to the microscope?
Yep.
So this collection of, is that like 10 lenses is our objective?
Yep.
Okay, interesting. Thank you.
So let's get a feel for this. Microscope objectives. When you buy a microscope objective, you never get, you will never see what's on that Zemax screen. Not just because of keeping stuff proprietary, but all of that stuff is fixed inside of something that looks a lot like this. And so what you get is you get something like this on the, they always look like this, and there's something threaded there that you screw in. You screw it into the microscope. All of the lenses are already securely mounted in here. This is the part that's looking at the specimen. This is the part that screws into the microscope, and beyond this is a tube lens. So if you just buy this, all you see is a little bit of glass out here, and if you were to look through this top end there, you would see, well, some glass again. So just looking at it with your eye, you'd have no idea that the real internal makeup of it may be something like this. All that you see is this. Or let me get a more magnified, more close up. Yeah, you just get something that looks like this or this, all right? And inside there, there's a whole bunch of lenses, but you never see any of that. You get this, you screw it in, and then somewhere up there, you put a tube lens. And again, the tube lens is probably already packaged with it. But if you're an expert user, you would customize it. If you're a more run-of-the-mill biologist, you probably just use it as packaged. But the tube lens would never be part of this. This you could persuade yourself, you could pretend blissfully that it's just one lens. The tube lens would be somewhere up there. So you're going to be adding a tube lens. Now, the rays, the tube lens, of course, if I've got an object here, then the rays, once I put this object at a finite distance over here and send it through the tube lens, the rays are going to go off axis. If I make a huge gap between my tube lens over here and the start of my objective, those rays could travel way far off axis and be up here before reaching that first lens. So we're going to want to put the tube lens pretty close. For practicalities, I would say put it a centimeter away, just because there's only so much room in a real microscope. Sorry, there's some things with the threads and everything, the way you screw it in. You can't just put something right smack up against it. But for convenience, let's maybe just put a centimeter from here to the tube lens. Then we'll have the tube lens. And then off to the left, we'll have the objects one focal length away. And so the objects will no longer be, the fields will no longer be measured by what angle they're at. They'll now be measured by an off-axis object height. I think the best way to go further with this is if between now and Thursday you guys spend a little bit of time playing with it in Zemax, then on Thursday we'll talk about the Airy disk, the Airy limit, the point spread function and what it means. And then we'll go back into this, and once you've had a little bit of time to play with ways of inserting the tube lens, then you can ask questions on Thursday. The alternative is that you can email me next Monday night at 10 p.m. with questions about inserting the tube lens, but not next Monday night because it'll be on spring break. The Monday night before, it's due at 10 p.m., but I can't promise that I'll be answering emails. So let's try to look at the table of tube lens parameters in the paper and play around with inserting layers here. And then on Thursday, we can do screen shares. Any other questions before we go?
So when we have like a telescope,
Yeah.
Do we need to do something similar, or do we already assume that the rays, because the object is so far away, they're already basically collimated?
With a telescope, you assume that they're collimated, but you still have two mirrors, a primary and secondary. And so the primary has a very long focal length, and so it takes that that very tiny angle and turns it into a very large off-axis displacement. And then generally the secondary puts that onto a detector. But there's still generally two. In principle, you could do it with one mirror. In practice, I think, again, I'm not a telescope guy, but my understanding is that they generally do two mirrors on the telescope as well, just to get even better magnification. The first one is huge, provides the wide baseline, the wide aperture that gets you the good resolution. And then the secondary helps you with the magnification and puts the light onto a detector.
Okay, and then if you're using one just with your eye, you have to use the two mirrors and then send that into a lens for your eyepiece, right? So,
in principle, the eyepiece could be a mirror, because all that's required is something that will take this image, the image formed by the primary, and turn that image into parallel rays at a large angle. A lens can do that, and a mirror can do that, and the mirror will do it without chromatic aberration. Now, there are old refractor telescopes, of course, do that with lenses, and there are some applications in field work with binoculars, or in the military with rifle scopes, where it would still be more practical to work in a geometry that uses lenses. But on a reflector telescope, I'm not sure if they have any lenses, or maybe they have one lens just for people to adjust their sight. But in general, most of the work is done by mirrors. And in principle, even the eyepiece could be a mirror. Other questions? All right, gentlemen, I will be available this afternoon during office hour time, and I'll see you again Thursday morning. Please play around with this in Zemax before Thursday. Take care.